Good afternoon, everyone. Thank you to the organizer, Xenia, Ibrahim, Jeff, for the invitation. It's a real pleasure to be here to celebrate Bob. And thank you for admitting someone hopelessly linear into the no linear zone. So let me start this presentation by remember when I first met Bob. I was a PhD student at the Institute of Optics, and the first professor I met was Bob, actually. I arrived from Mexico, I arrived a few days earlier, and I went to the professor's offices to find out what books we were going to use. So I remember, well, the first door I knocked on was Bob's door, and alphabetical, that's right. And I remember that I asked him, so what book, this was for the radiation and detectors course. So what book will we be using in the course? And he said, my book on radiation and detectors. And I remember this because right after that I went to see the next professor, Warren Smith, who was teaching geometrical optics, and I asked him, what book are we going to be using? He said, Warren Smith's book. And I thought, okay, people write their own books here, but at least Bob speaks of himself in the first person. Then I found out that Warren's book, there are two Warren Smiths, so the one that wrote the book and the one that taught the course. So many years later, about 2 years ago, Bob asked me a question, which is the motivation for this talk, which is the following. Is the geometric phase dynamic in origin? Now this was in Rochester. Had it been in Ottawa, of course, Bob would have had to ask the same question in French as well. So I don't have an answer yet. I'm going to try to give a partial answer at the end of the talk. But somehow this question 2 years ago was a premonition of things to happen to me. The last year, for some reason or another, geometric phase has been following me wherever I look. So in the last year, I published several works to do with geometric phase, so I'm going to describe those a little bit. Before I move on to that, I just want to mention that another thing that I'm very grateful to Bob for is that he's been a great mentor to many Mexican students. And I think in part that is because he likes to practice his Spanish. So yeah.
He said Mexican students work the hardest.
Yeah. And those that speak Spanish amongst you can recognize that I gave Bob a Mexican accent. Okay. So what is this geometric phase business? So well, geometric phase is a universal phenomenon in physics. Whenever you have a wave field propagating and that wave field has some extra degrees of freedom, as it propagates, it accumulates a dynamic phase that has to do with the distance it propagates, the optical distance in the case of optics. But if one can associate a parameter space that is curved with the extra degrees of freedom, for example, polarization, and if this propagation involves a transformation that encloses an area in this curved space, there's an extra phase, that is the geometric phase. And in optics, there are at least 3 instances where this happens. One is when you have light propagating just paraxially in one direction, but it changes polarization due to the action of polarizers or retarders. There's also polarization if light is paraxial, but you change its direction and then bring it back to the initial direction. There's going to be a change in the polarization. And finally, not involved with polarization, if your beam has a mode structure, and that mode structure can be represented in a curved parameter space, there's an analogous geometric phase that you can accumulate. Now, you might be wondering if I made a mistake here. No, this is the order in which I will be talking about these 3 topics. That order didn't make sense in this slide, but these 2 involve polarization. This one does not involve polarization. So this is a figure, for example, from Michael Berry's paper, one of them, explaining this. So in the case of polarization, this curved parameter space is a Poincare sphere that I'm going to describe in a second. For redirection is the sphere of directions. And then for a model structure is another type of Poincare sphere. Okay. So just a quick refresher. I don't think I need to spend much time on this here, but if you have polarization in the XY plane, it's parallax light propagating towards you. The ellipse can be represented by two parameters. One tells you how round or flat the polarization is and whether it goes to the right or to the left, and is described by that angle theta that corresponds to latitude on a sphere, for example. And the second one has to do with the orientation of the ellipse, and that can be represented as longitude on the sphere. So this parameter space is naturally a sphere, and it represents the polarization of monochromatic light. Now, what happens when you have birefringence? Well, I was looking at this with my student Anthony Vela, who, by the way, defends his thesis on next Tuesday. And we were studying spatially varying birefringent devices, so things like, I have a few of those here, like SLMs, Q-plates, metasurfaces, or stress materials, where you have different birefringence at each point. So we were part of his thesis was on designing devices for different applications where we use spatially varying birefringence. And so we came up with a geometric description for spatially varying birefringence, and as a side effect, we thought a bit about geometric phase. So I'll skip the details of this spatially varying birefringence description. Let me just show you that you can represent the birefringence at one point by a vector inside of something like the Poincare sphere. So you have two eigenpolarizations. These are the polarizations that come out the same way they go in, and they can go in different directions. They need not be linear, so you can have it in different directions. And then there's a retardance, 2 delta, between the two. And if there's no retardance, then we represent that as a radius in the sphere. So if there's no retardance, we're at the center. If there's halfway retardance, we're at the edge. And the effect of this birefringence on an input polarization is that if the input polarization is this red dot, for example, the output polarization would be a rotation around this axis by a certain angle. And that angle depends on this delta. So the bigger this delta is, the bigger the angle. So halfway plate is 180 degrees, and you have different angles. There's a nice geometric interpretation for this angle. So if I show this angle of rotation happens to be related to the length of the vector by the angle subtended by this projection here. So in any case, you can represent birefringence as a point in the Poincare sphere. So when we were looking at this, and the idea was that we're looking at a spatially varying polarization sphere, so I can show you quickly here. Now if we have a spatially varying birefringence, then we would have for a device some distribution inside of this sphere. But then the question came, I presented this work before we published the paper in Capri in the meeting, and one of my friends, Costi Ablio, asked me, what about geometric phase? So I said, yeah, what about it? And we thought about it, and it turns out to have a very nice interpretation in this context. Suppose that you have an input polarization, which is this point in the Poincare sphere. And we apply some birefringence represented by this vector that gives us a rotation around that vector. So I rotate around and I get to this other point here. Then I apply a second birefringent material to bring it back to the initial polarization. So I come back this other way around this other axis. Now, normally when we talk about geometric phase, we always know this thing that the geometric phase is proportional to the solid angle enclosed by this path. That is not true in this case, because we don't have what is called parallel transport. However, that phase has a very nice interpretation we found, which is, if I take this and I look at this sphere from the point of view of the input polarization, that is, I put that red dot right at the center, and then I look at these two vectors that define the two birefringences, they're away by some angle in this projection. That is the geometric phase. So the geometric phase happens to be that angle between things. So I can show you this. If I move it around, I show that projection along this line between the two vectors, and the angle between them happens to be the geometric phase. So even though we don't have parallel transport, we don't have a solid angle connection, there's still a geometric aspect of geometric phase. Okay, so that is after I published this paper, unfortunately, I went to a meeting in Quebec a couple of months ago, and I ran into my friend Johannes Courtial, and he told me that he had published a paper with a different geometric interpretation many years ago that I happened to miss. It's a very different interpretation, and I'm working on showing geometrically that they are equivalent. But mentioning Johannes is a good segue into the second part of the talk, which is modal structure. So Miles and Johannes published a paper many years ago proposing a Poincare sphere to describe not polarization, but modal structure. So if you have a Laguerre-Gaussian beams of the lowest order, say the right-handed and the left-handed, you can put them at the poles of something like a Poincare sphere, just like you put right and left circular polarization, and then any linear combination of those lives elsewhere in the sphere, and on the equator you have Hermite Gaussian beams with different orientations. Now this idea has been generalized for higher order beams, so you have any, whoops, something happened here. Any Laguerre Gaussian beam, doesn't matter, and on the edges, on the top and bottom, and then Hermite Gaussians on the equator, and then different beams in other parts. Those are no longer linear combinations. So with Mark Dennis, we looked at understanding structured Gaussian beams from the ray optics point of view, because that turns out to reveal a lot of nice aspects about it. So let me show you how this works. So these beams, the Laguerre Gaussians or Hermite Gaussians, have the property that as they propagate, they look the same, they just get slightly bigger. So if we want to think of rays that do the same thing, well, we have families of rays like these ones that describe an ellipsoid like this, is squeeze, and the cross-section is an ellipse, and it's the same as it propagates, just gets bigger. And this ellipse can be more flat, or can be go in the other direction, for example. Or it can point in different directions. So this suggests an interpretation using a Poincare sphere, because Poincare sphere is a parametrization of ellipses. We're not talking about polarization, but we're talking about ellipses. So this ellipse happens to correspond to this point. Now, to build a Laguerre Gaussian beam, for example, we need not only this family of rays, we need more. So I'm going to take families of rays all with the same total angular momentum, which happens to be the vertical coordinate on this sphere. And then, so it's all these sets of rays. And actually, I'm going to put them together. So if I put them together, I get a nice beam like this. And then changing the radius of this circle over the Poincare sphere is something equivalent to changing the p order of the Laguerre Gaussian. It makes it thicker or thinner. So what we see in this representation is that a beam is not a point on the Poincare sphere, it's a curve. And these Laguerre Gaussian beams are a circle. Now, I can send these beams through pairs of cylindrical lenses, and that has the effect of rotating this sphere. Whoops, okay, better hurry. So you can rotate it, and you get, for example, to a Hermite Gaussian beam. Now, this picture gives us an inspiration for geometric phase, because suppose now that I take this beam, I transform it through cylindrical lenses. I go to the south pole, so I go through a Hermite Gaussian, south pole, and then I come back a different way. The beam acquires a geometric phase. Now, the beam is the same, but what is different between the beginning and the end? The rays are at a different point. The rays, the global configuration looks the same, but the rays are at a different point. Look at the colors, initially and finally. It's like having a troupe of folk dancers that do a fancy dance, and at the end they come back together to the initial position, but each dancer has moved around. By the way, something similar happens with the GUI phase, but I should. So based on that idea, we propose a way to measure the geometric phase without interferometry. You take this beam, and suppose, using the dancer idea, suppose that there's a bus strike, and only this group of dancers shows up to rehearsal. After they do their dance, they end up here. So the intensity of the beam is going to be different, and just looking at the centroid of that intensity gives us the geometric phase. So there's a way to measure we compare this in experiment with an interferometric measurement, and of course we get the right result. So here, geometric phase is purely geometrical. It's a switch of the rays composing the beam. Finally, let me talk briefly about redirection. So in paraxial optics, we represent polarization by the Poincare sphere because the polarization ellipse is constrained to the XY plane. But if we go non-paraxial, the ellipse can go in any direction. So all three components of the field play a role. Now, John Hanna proposed borrowing a construction from Majorana for spin states. And in this case, because the field has three components, we can use 2 points on the sphere. And this picture sort of represents how this works. So 2 points gives us both the plane of the ellipse and its ellipticity. This works very nicely for many purposes, connects nicely to some mappings, but it doesn't work nicely to connect with geometric phase. It's a bit convoluted. So in very recent work, I'm just reviewing one of the last drafts now, it's a paper with Mark Dennis and with Kostya Bliok. We're looking at aspects of non-paraxial geometric phase, and my personal contribution was to try to think of an alternative representation of geometric phase in terms of a sphere. So what we do is we take Mr. Majorana and his construction, but we put some aspects of Poincare in him, and that gives us a sphere that connects precisely a path on this sphere, or a pair of paths. The area enclosed gives us a geometric phase. So let me just finish by showing you that. So if I take this example here, in this Poincarana, we call it for the moment, I don't know if that's going to be the name on the paper, I have an ellipse, and it evolves both in orientation and in ellipticity. And according to this description, the ellipse is described by these 2 points. And as we move around, we end up enclosing some areas, and these areas are proportional by a factor of 1/2 to the geometric phase acquired in 3 dimensions. So this construction generalizes the Poincare representation. And with 1 minute to go, I just want to finish by trying to answer Bob's questions. So is geometric phase really geometric? Well, for redirection, it is, because it's just a geometric rotation. There's no delay. For polarization and birefringence, things are trickier. If we have birefringence, we are retarding one component with respect to the other. We send a short pulse, we will be delaying one component with respect to the other, except for the case that we mentioned with polarizers. Otherwise, the division between dynamic and geometric is trickier. But for mode transformation, I think it is truly geometric, because it does have to do with the change of the position of the rays, at least very optically, not with their optical path lengths. So with that, I just wish you, again, a happy birthday. I thank my collaborators and the funding agencies. Thank you very much.
Bob, do you have any questions?
Oh, just real quick. So I love to talk, and we should talk more, just the 2 of us, or in a smaller group, about the mode transformation.
Okay.
Because that's the one I understood the least. Well, I hadn't thought of it. So we'll talk.
Okay,
Great.
wonderful. Thank you.
Sure.
Okay, one last question. Ibrahim.
So the last one was amazing. All part was amazing, but the last one was the question regarding the equine, right? So if you apply this to the Mobius space, right?
I have the slide for you, so I was. So can you project it just a second? Yeah, I knew you were going to ask that question. So if I come here, so this is the case, that a non-Mobius case. If you have a Mobius case, then we have more something like this. And after we come back, rather than 2 loops, we have 1 loop. But the solid angle enclosed by that 1 loop is still the case. And we're studying cases where there's a transition between one case and the other. Okay.
Okay, let's thank Alonso again.